right, guys, let me see. Somebody right here help me with the data points. I gave all mine away. Was it 2?
2, 4, 5, 6.
There's 2 6s?
Yeah.
2 7s?
8, 9,
2 10s? Okay, sweet. Thank you. We can do it. And then when you do the mean, you get the sum of those is 78 divided by 12. What's n always represent for us? What's n always represent? The number of data points. See, so sometimes math people, we pick the right letter. N, number of data points, kick ass. I like it. So once I do that, I get 6.5. So I want to take all the stuff in L1, and I want to take 6.5 away from it. Bam. So most people got that. And then if I move over here, I'll want to take everything in L2 and stay with me now. Square it. Okay. So I was a little evil, and it's just in my nature. But let me just show you a quick way to add stuff up in a list. Hit second quit. Do you see somewhere that says list?
Stat.
Yeah, so if it's second stat, it takes me into the list stuff. I could do shit to my lists. I want to do some math on my lists, right? I want to add some of them up. So I want to sum up. So I can say sum up L2, 0, like it should be, right? And the nice thing is once you put something in, I want to sum up L3 now, don't I? I'm not going to go back in the list and all that shit. I'm just going to hit second enter. And then go back and put L3 in instead. See that? Is that cool? Second enter kicks so much ass. It just brings back up the last thing you did. So I saw most people got that. That's the sum of the third list, right? Okay. I like it. Somebody got worried. Okay, I like it. Now take 69 divided by 1 less than 12. What's that?
That's
No. I can see what it is. Well, what is it? Variance. I like it. Now, on your paper, you can write down a rounded version of that. But if I'm not done calculating stuff, I don't want to round. So how do I do that? Well, you hit square root, and I don't know if you guys remember, I'm pretty sure I said this. That little button right there kicks so much ass. It's temporary memory. It always has the last number that was on the screen. So if I hit second negative and get square root of answer, I'm going to square root that whole thing. Bam! So I don't have to write all that shit in there. Say again? No? There you go. So truly round that bad boy to at least 3 places. So if you use 25045, that's awesome. Just don't use the whole thing, but round it to at least 3, if not more, decimal places. So I would use 2505.
I was curious, I don't know if you were to answer this, but why specifically why that one you want it to be so to the 3rd place?
So there's an idea that I could teach called significant figures. And if you've taken any science, you might have hit some sig figs before, and you can realize how that can be kind of a time-consuming topic, right? So if you're not going to take any science, I figure I don't really have to get too deep into that. Going 3 places on standard deviation at least normally takes care of any rounding errors for the most part, right? So you could get a little more specific about how much to go in certain situations, but I just try to make it a blanket 3, because if you go 3 places, that's normally enough to not have too big of a rounding error. Is that all right? Okay. The bigger general idea to get is don't round anything too much until the end of a problem. Because if you round in the middle of a problem, you do extra shit with that rounded number, you're going to go further and further and further off from the right answer. Here's you. Here's the right answer. Ah, shit. Yes?
So what if you just write like copy paste off the right answer, you don't fill in the blank.
Do it again.
So you see how you got 6 point whatever that
Yes.
number is. So if you answer that and then you don't round until like you don't round it off and you just like get to the bottom number and then you do this math and everything would still be wrong. If you don't round
Oh,
it
if
at
you
all.
use all these digits?
Yeah.
It's that would be like better in one sense, but like shit, why? I don't need to see all that. But no, it's beautiful. All right, that's fantastic. All right. So notice what I said. Round standard deviation to at least 3, if not more places, right? So I want to see how many people are going to be given like 11 decimal places. Okay. Now, the questions I ask. What was the first thing? Oh yeah. So we got that all done. Oh, and then there's something about this. How many standard deviations from the mean to the data point? All right. By the way, we're going to take a break when we're done with this worksheet, okay? Okay. So just to lay some groundwork. This is huge. Standard deviation is one of the first most important ideas to get. And the reason it's so frickin' useful is it's kind of like a natural unit of distance to use. So if I wanted to prove, if I made a drug, so Tylenol, let's say Tylenol takes like 20 minutes on average to alleviate your headache. Let's just pretend like that, okay? And I make a new drug, and I want to show that it alleviates headaches quicker, right? And I do a sample of people and I give them my new drug and I get something lower than 20. It's got to be, it can't just be lower, it's got to be a lot lower to be evidence that I did make it lower. Because it's just a sample of people. Maybe there just happen to be people that their headaches go away faster. So I want to be able to show a claim is true by showing something is really far away from. So if I'm like, somebody says, no, yours is still 20. I'm like, no, I think mine's less. I got to get a sample that has really far away from 20 to be evidence that my drug does work faster. So how do I measure distance in statistics? How would I measure how far apart things are is standard deviations. So for example, if I was going to ask you to measure the distance between two people sitting next to each other, would you use miles? No. Could you? Hell, 0.0007 miles. What would you use? Since we're in America, we use inches, right? Everyone else in the world we use centimeters or something. But if I wanted to measure the distance between two planets,
Light.
I could use light years. I like it. Astronomical units, which you might not know. Or, miles might be good enough, right? But even then, you're getting pretty big sometimes, right? You guys kind of with me? So standard deviation is kind of like a natural unit to use for distance. So if I said this data point is 3 standard deviations above, if your grade was 3 standard deviations above the average, damn, you scored you're really far away. Shit. Right? And of course, right now we don't have a feel for, why is 3 such a far away, Jeff, but we're going to get that really soon. But it's how I measure. So if I'm like 0.1 below the average, I basically scored average, right? I'm not that far away from the average. Are you with me? If I'm 0.1 standard deviations below the average, I'm really close to it. So if I have data that looks like this versus data that looks like this, right? These two data points are much further away than these two on this one. These are much further away because the standard deviation is so much smaller. How do I say this? In a small town, or like have you ever visited a university and gone on a tour and been like, oh my God, I hope I don't have class on that side and then another class on that side, and I've lived that experience, right? And then you come to something like Grossman College, it's big, but it's not like, all right, it's not a big deal. If you think it's a far way to go from one side of this campus to the other, you have not been to a university, for example, right? So if I was talking about the distance between two classes, at a university, they could be from the entire length of one side of Grossmont to the other apart, and I would say they're close because the whole university is so spread out. But at Grossmont itself, if I was here and my next class was on the other side, I'd go, man, that's a far way to walk. Because relative to how close things are at Grossmont, that's a huge distance. Whereas at a university, relative to how far apart things are, that's not a huge distance. I like it. So here's what standard deviation is. Standard deviation would be the tick marks on a ruler. So for us, what was our standard deviation? 2.505, right? Every ruler mark would be 2.505 apart. And this this question C, is me putting the ruler down and measuring how far apart those two things are. So let me ask you this. All right, so I'm at the 10 mark, right? Stay with me. And I say every step I take is 2. So every step I take, I go 2 on this scale. You with me? How many steps to get to there?
Wait, it's 2?
Every step I take is 2. So if I took 1 step, I would be at 12. Right? Bam, there. How many steps to get to 15? 2.5. Kick ass. How do you actually get that mathematically every time? I made them relatively nice numbers, right? Well, how far do I have to go? Total. 5. How far do I have to go? X minus the mean, or X bar here, right? Divided by how big each step is. In this case, it was 2, I said, right? And that would be, so this is the data point where I want to get to. So for you guys, it was 9. Minus the beginning point, the mean, divided by how big each step is, the standard deviation. So very often I will reference standard deviation with the word step. Don't write that down when you answer a question on a test. I need you to say standard deviation, but in talking about it, it is like stepping around.
Why did you say the beginning point is the mean?
So very often we consider the mean to be where things should kind of cluster for most things. So if I had to take a guess, even if there's not anything near the mean, if you had a guess, if I told you the average age of students here at Grossmont is 26, and I say there's a student over there, guess what his age is? What is your absolute best guess? 26, right? Isn't that your best guess? I'm not letting you look at him, so don't say I can take a look. No, you can't see this person. You with me? The average age, please be with me. The average age of Grossmont students is 26. You just know that. It's exactly 26. It is. And there's a person coming behind you. Don't turn around. What's your best guess of how old they are? 26. You guys understand that? I like it when I look at somebody, their head goes, oh. Oh, come on, please. Well, what else could it be? Why would it be more likely? Why would it make more sense to be up or down from 26? That would be your best guess, wouldn't it? Are they 26? Would you put money on them not being 26? I would. They're probably not 26. But what's my best guess? Freaking 26.
I thought that it was on like a scale, so like the mean would be in the beginning, like in the middle.
Yes.
And then anything that's like, say like the lowest possible, like our lowest number and highest.
Lowest age? Sure.
And then the mean in the middle, obviously.
Of course, yes, totally.
So why don't we set it up like that?
Because here's the way it works. You have the mean, and then you can go away from that mean up or down. So very often we consider the mean to be our starting place.
So you're just looking at.
So we start with our best guess. And then if I told you, oh yeah, that guy has to take the lowest level of math, then my guess would probably go down from 26. Now, is it definitely sure that he's less than 26? No. But why would I say he's probably younger than 26? Because most of the people coming out of high school are younger, will have to start off lower level math, right? Now, is it possible he's older than 26? Shit, yes. But my guess would go down from there because I'd have more information. But without more information, my best guess is the average. Are you guys semi with me? A little bit? There's a game on The Price is Right. Stay with me. Has anybody ever seen The Price is Right? I know it's freaking Drew Carey, whatever. I remember Bob Barker, when I'd stay home from school sick, I'd watch a stupid show. And they have blank spots for the price of a car, right? 1, 2, 3, 4, 5. My day was 4, but that was. And you have to guess a number, and based on how far away you are, you have to give some money. So a gambler wouldn't do this, but the best guess for any of these is 5. Because it's going to be the closest to anything else generally, right? Now the first number, you wouldn't say 5. You with me? Because I know more information about the first number. The first number is more than likely 1 or 2, right? But any of these other numbers could be anything. So what's your best guess for what that number really is? 5. Why 5? It's the average. It is the thing that is closest to everybody. Are you going to win if you guess 5 on everything? No. So you do have to become a gambler. I don't know if you've ever seen. Has anybody ever seen that game?
Yeah.
You start off with so much money and how much you're off you got to give, and they give you enough money so you can't just say 5 across, of course, because then everybody would win and they have a lot of cards they have to get and give away. You guys semi with me? So your best guess in any situation, absent more information, is the average. If you turn around and look at him, he's got gray hair and wrinkles, you're not going to say 26 unless he's had a really rough life, right? You're going to guess more than 26. With more information, you can be better. No information, average is my best freaking guess, right? Certain time of day, I took the temperature. What was that temperature? Was it, I'm not going to say anything else. Oh shit, I'm just going to tell you the average. That's the closest I can get without any more information. Okay, I think I've beaten that topic to death. Okay. That's why we consider this to be the starting point, and this measures how far away I got. So can this come out negative? Shit, yes. Right? Now in this example, what was it? Our data point was 9. X represents the data points. I want 9. The mean for this thing is set. What's the mean? 6.5. And the standard deviation we just calculated. And why does it make sense it comes out to be almost 1? Because 9 is almost 1 step above 6.5, right? So you got 0.99. Okay, I like it. Almost 1 because it's almost 1 step up. Is that making sense? So what about, let's do another one. What if the data point was 3? Somebody got a 3 on this thing. Right? They got some problems. Oh, made up for that. There you go. Well, let me go ahead. This thing is called the Z-score. Right? Sounds like some kind of anime thing, but it's not. Z-score. Go! Right. So this formula is the Z-score. If it was a population, I could put mu there and sigma there. Cool. Doesn't really change the formula, it just changes the symbols I use. So what if I wanted for 3? What would it be? Be 3 minus 6.5 divided by? Yeah. It's like 1.4, negative 1.39. I probably did that too quick. Anybody gonna help me? No? Yeah, you're on your own, math boy.
Yeah.
Come on. What is it?
Negative 1.39.
7.
Oh, shit. That was close. Negative 1.397?
Yeah.
Okay. All right. So it's almost 1.5 steps. You see that? It's almost 1.5 steps down. So if your Z-score is negative on a test, that is bad. You scored below average. You with me? So Z-score is a distance, but why is it allowed to come out negative? Because it tells me what side of the mean I'm on. That's it. Is that cool? Or understood? It doesn't have to be cool. Yes? Well,
Okay, sorry. Is it like, so it goes the distance either way, right?
Yes.
So like, we'll go 1
yeah, okay. This does relate to the quartiles in a way, right? It's its own idea, but you can sort of relate it to the quartiles. Not quite yet, though. Yeah. Okay. All right. Okay. So you're cool with that? So ours, you should have gotten 0.998. And then that last question really captures this thing we just talked about, that the mean is in the middle. So now watch this. Let me say this before we get into this problem. Anybody remember what that's called? Bell curve. And we're going to call it, in this class, we're going to call it a normal distribution. Normal distribution. Notice how most of the data is in the middle. Right? It's got a big old belly. It's laying down. Right. So let me tell you a few things for sure about this. Let me see if you guys are cool with this. Let me say the mean is 40. And the standard deviation is 3.5. Cool? So we just know this. What's one step up from the mean? One standard deviation up. Yeah. Is that cool? What's one step down? Yeah, 36.5. Now watch, I'm going to write something underneath those things I've written already. See if you guys see what this means. What are those in blue? The number of standard deviations, so those are z-scores, right? The z-score for this is 1. Why? Because we freaking added a step to get up to it. So of course it's one step up from the mean. That's how we got it. You with me? 43.5. How many steps up from this is it? 1. Because that's how we got it. We went one step up. This is one step down. What's 2 steps up? Oh, my picture's all off, but oh well. 47. And what's 2 steps down? Yeah, there. 30. 33. I like it right here. This is already half it. You guys kind of with me? A little bit?
The z-score is just like how many standard deviations it is from the mean.
Bingo. So when you say it on a test, I want you to say it exactly like that. In class, I will sometimes say, this is 2 because it's 2 steps up. What's each step though? Standard deviation. So if I had this area to search for a missing child, right? And let's say the area is as big as this room, but there's a lot of shitting. I'm going to take little steps, right? If the area I've got to search is a huge field, I might take more steps. So if my data is not very spread out, if my data is like this, and I take a big ass step, I missed the whole thing. I missed everything. It's like if you're traveling down a big interstate and you blink your eyes, you sometimes miss a town. If you never, like, there was a speed limit change back there, holy shit. All right, so if you ever driven long distances, it's like slow down, town lasts for like 3 seconds, and then speed back up, right? Sometimes if you blink, you missed it. So if you take too big of a step, you're gonna miss everybody. So if I want to investigate this data, I want to take little steps. That's this. Because what would be the difference for this guy? If I want to investigate him, I want to take bigger steps. Does that make any sense? This isn't like the official explanation of shit. This is just the way I look at it that makes it make sense to me. There's other ways to look at it. Okay, so if it's a normal curve, there will be 68% of the data in there. If it's not normal, I don't know. Could be anything. So for this problem we did, it's not normal. If you did that last problem, you shouldn't have gotten 68%. If it's normal, there's going to be 95% here within 2 steps. So we are going to define what is usual or what's like unusual. So how would somebody be unusually tall if they were more than 2 standard deviations above the average height? Then we officially consider them unusually tall. Do you see how this is an outlier idea now? So now that we have this idea of distance, I can better define what outliers are. So 2 steps away in both directions catches like almost all the frickin' data. So if you're out here, you are rare, right? You are unusual. So if you saw somebody down here, if you saw some dude that was 4'2", you're going to try to be polite, but as a human, you're going to go, I don't see that every day. I'm going to look again because I don't see that every day, right? See it on TV. Okay. I don't mean to sound like, no. But that's why we call it unusual. It's not something I would expect to see. And why is it? Because it's only got a what percent chance? What percent of the people would show up out here? 5%. So we just decided, it's sort of arbitrary, but it's a decent thing. We decided that would represent unusual. 5% is a pretty, less than 5%, that's an unusual thing to happen. Yes, I love it. So what percentage would be up here? 2.5%. Because one thing about the normal curve is it's symmetric. Right? So it's, if there's 5% total outside, what's on that side? 2.5. Kick ass. Okay, so now this last question I ask might make a little more sense why I ask it. This is theoretically what will happen for a normal curve. On this one then, I say put the mean in the middle. What'd you get when you went down a step? 3.9, blah, blah, blah. And what'd you get when you added a step? 9.0, blah, blah. And then I like to do this for myself. What data points did we catch in there?
Only 90 different.
Which data points? You caught all the 4s, right?
All the 4s, 5s.
All the 5s, all the 6s, 7s, 8s, 9s. And how many data points total is that? Not 1, 2, 3, 4, because there's multiple things, right? So you got how many data points? 9. Is that cool? How many data points did this catch? 9. Because the 10s are out here and the 2 is down there. So what's true about the person that got a score of 2? Is that an outlier?
Yeah.
How do you... This is an evil question. How many steps did I take? 1. Outlier started at 2 steps. I'd have to take 1 more step up and down. So it actually turns out that there are no outliers in this one. All right, that was a little evil. I'm sorry. Got to get that out of my system. So there were 9 data points out of 12. So what percentage did I catch?
75%.
75%. If it was normal, it should have been 68%. All right. Woo! So that kind of question, that last question on this sheet, I'm going to ask it several times throughout the semester because we're going to experience different distributions of data. We're going to calculate means and standard deviations. We're going to be able to do this in different situations. So you're going to see this question over and over and over. All right, let's take a break. What time is it? Let's come back at 20 after. Yes. Oh, yeah.